One of the truly powerful things about KSP is that we can use it to solve the concentrations of ions in a saturated solution. And because of this, we can actually make predictions about that solution, we can manipulate them to our own uses, and we can just understand solubility that much better and have much more effective productions when it comes to using chemistry. That being said, for students who first start using KSP, when they come to questions like this, it often seems like you don't have enough information. And when you see how somebody solves it, there's an underlying principle that often gets left out. So what I wanted to show you is how we actually solve these problems and the principle behind it that comes from an icebox. And then after we do it using an icebox, I want to show you how you never actually need to use an icebox ever again for a KSP problem. So to understand this, let's take a look at this example. The KSP for magnesium carbonate at 25 degrees is 2.0 times 10 to the negative 8. What are the ion concentrations in a saturated solution at this temperature? When you read through this question, most students feel like they don't have enough information because you're given one value. You're given the KSP, but really that's enough for you to be able to do this. So let's take a look at how we would solve it. So when it comes to this question and dealing with KSP, what I want to show you is how we use an icebox to actually come to the answers. That being said, once we do the icebox once, you'll see why you never have to actually do it again if you understand the principles. But we need to start with a balanced equation, and since we're dealing with dissociation, that's the equation we're going to use. So we're going to write out our dissociation equation. So magnesium carbonate as a solid is in equilibrium with magnesium ions that are aqueous, and that's also in equilibrium with carbonate ions that are aqueous. Now I said we're going to use an icebox to solve this, so let's build our icebox. So I need to make a column for each of these substances. We know that we're trying to find the actual concentrations, and we know from the question that the KSP is 2.0 times 10 to the minus 8. Now we want to set up our icebox, so we make our 3 rows, one for initial concentrations, one for change in concentrations, and then one for equilibrium concentrations. Okay, before we go any further, keep in mind this is a solid. Solids have no effect on equilibrium. So we actually don't even need this column at all. I'm going to cross it all out. And we're just going to be dealing with these last 2 columns. Keep in mind when we're dealing with products, their initial concentrations are 0 unless otherwise stated or you know some more about that solution. But starting out with these problems, you're going to be dealing with concentrations equal to 0. The other thing we know here is these concentrations have to increase. We know they have to increase because they have to go higher than 0. And we don't know by how much, but we know it's by some factor related to their coefficients. And we're dealing with 1-to-1 ratios in this problem. So it's just increasing by a factor of x. So that means at equilibrium, magnesium just has a concentration of x. And carbonate just has a concentration of x. So since those are our equilibrium concentrations, we can actually just plug those into KSP. Because remember, the KSP is just going to be the concentration of products raised to their power of their coefficients multiplied by each other. Now in this case, the concentration of magnesium is just x. The concentration of carbonate is just x. And the only other thing we need to know is the KSP, which was given to us in the initial question. It's 2.0 times 10 to the minus 8. Now x times x, that's the same as writing x squared. And the only thing that we need to do in order to solve this question is take the square root. So the square root of 2.0 times 10 to the minus 8 is going to be 1.414 213562 times 10 to the minus 4. Now we want to keep two significant figures because of the KSP having two significant figures. So x is going to be 1.4 times 10 to the minus 4. So then what's our concentration of magnesium? Well, the concentration of magnesium is just x. So it's 1.4 times 10 to the minus 4 molarity. What's our concentration of carbonate? Well, it's the same as magnesium because it's a 1-to-1 ratio. So it's 1.4 times 10 to the minus 4. That's our final answer. Now, the one thing I had mentioned is that you don't actually need to set up the icebox. The icebox is the underlying principle. But let's think this through for a moment. Products are always going to start at 0. So that means the only thing that this relies on is the change. And the change is always going to increase because you're always going to start at 0. And how much it's going to increase is always going to be based on the coefficients. So whatever the coefficient is should be multiplied by x and plugged into the equation. When you're dealing with a 1-to-1 ratio, it's just going to be x multiplied by x. Let's pretend for a moment that this was a 2. I know it's not, but let's pretend. Then that would make us put a 2 here. It would make us put a 2 here. It would make us square this and have a 2x squared in the brackets. Now that's not what we did here, but you can see how it's all just based on the coefficients. So if you understand that underlying principle, you can actually get away with never having to do the icebox. And literally just starting at this point, filling in your question, and then solving. And that's what I'm going to show you how to do in my next video when we no longer have a 1-to-1 ratio and we're dealing with something a little bit different. So thanks for watching, and I'll see you in the next video.